When they are energy harvesting, they are doing it with the LoRa. So why don't we Google, what is the LoRa? And we're going to click on this link. What are LoRa and LoRaWAN? Welcome to the first chapter of the Things Fundamentals on LoRaWAN. In this section, you'll learn why LoRaWAN is so awesome, hear about some great LoRaWAN use cases, and learn the difference between LoRa and LoRaWAN. LoRa is a wireless modulation technique derived from chirp spread spectrum technology. It encodes information on radio waves using chirp pulses, similar to the way dolphins and bats communicate. LoRa modulated transmission is robust against disturbances and can be received across great distances. Don't be alarmed about the complex terms. LoRa modulation and chirp spread spectrum technology are simple to understand and practice. In case you are curious, in this video, Richard explains how chirp spread spectrum technology works. And we're going to watch this video.
A plain radio signal carries no information, apart from the fact that the transmitter is being left on. The signal has to be modified in some way to be used to convey information, and there are a number of ways in which this can be done. Two of the most popular methods are to modify the amplitude and the frequency, and these will be familiar from the fronts of the traditional radio, AM and FM, amplitude and frequency modulation. Listeners to AM radio will be aware that it's more susceptible to interference from natural and man-made sources because it's not as sophisticated as FM, which is clear and resilient, and is a more complex and unnatural waveform. AM and FM will be easily recognised because of their widespread use in broadcasting. Here, we're not concerned with music and speech, but just binary ones and zeros. Digital 1 and 0 signals could be sent using AM by just keying the signal on and off. Crude but effective. With FM, one frequency could be used to represent a 1 and the second for a 0. This is also a common method and called frequency shift keying, FSK. We can see this signal jumping between its two frequencies here and recorded below in what is called a waterfall display. FSK is important as it's simple to produce and detect and is referred to in LoRa radio transmissions. But LoRa goes further and in doing so becomes more complex and even more resilient to background noise. Rather than just use the two frequencies of FSK, it sweeps between the two like this, up and down. Now, there are two parameters that may be changed on both the rising and falling signals. These are the rate at which the sweep changes, call this the sweep rate, and the range over which the sweep could change, call this the bandwidth. There are always compromises in communications, and here there are compromises in both sweep rate and bandwidth. Increasing the bandwidth provides a better quality signal, but bandwidth is at a premium. Everybody is vying for space, and bandwidth is valued and restricted. Engineering involves maximising performance using minimal resources. Bandwidths specified for LoRa are therefore restricted under international agreement to 500 kHz, 250 kHz and 125 kHz, and in Europe further restricted to just 250 kHz and 125 kHz. A slow sweep rate is easy to decode and becomes progressively more difficult the faster the change. Here's another potential trade-off. The faster the sweep rate, the more information can be passed, but the more difficult it is to accurately resolve the signal. The European system uses 6 different sweep rates, or spreading factors as they're referred to. These are referenced by numbers 7 to 12. We've already seen that LoRa devices use a LoRa, which is a protocol where any device can just wake up and transmit, regardless of any other existing conversations. As an alert, a device will start by sending this unique training cycle of 8 up sweeps followed by 2 down sweeps. We can break these sweeps into symbols of equal period. The block of 8 is called the preamble and followed by 2 symbols used for timing, called the synchronizing symbols. Any listening device can clearly recognize this preamble as the beginning of a packet, which alerts its attention. The transmitting device is then time limited by which it must complete the rest of its transmission. All of the data content of the packet is contained in the following symbols. Each symbol contains a discrete frequency step representing 8 bits. The data contained in each sweep is probably best shown using these examples. The details, like all good comedy, is in the timing.
LoRa is ideal for applications that transmit small chunks of data with low bit rates. Data can be transmitted at a longer range compared to technologies like Wi-Fi, Bluetooth, or Zigbee. These features make LoRa well suited for sensors and actuators that operate in low power mode. LoRa can be operated on the license-free sub-gigahertz bands, for example, 915 MHz, 868 MHz, and 433 MHz. It also can be operated on 2.4 GHz to achieve higher data rates compared to sub-gigahertz bands at the cost of range. These frequencies fall into ISM bands that are reserved internationally for industrial, scientific, and medical purposes. So again, these are reserved internationally for industrial, scientific, and medical purposes. Now let's look at LoRaWAN. LoRaWAN is a media access control layer protocol built on top of LoRa modulation. It is a software layer which defines how devices use the LoRa hardware, for example, when they transmit and the format of messages. The Things network is powered by the Things stack, which is a LoRaWAN network server that receives messages from LoRaWAN devices. If we scroll down, we can see them talking about bandwidth versus range with this lovely image. Now we're going to go over here and read this article. What are the advantages of LoRaWAN over Wi-Fi? LoRaWAN, which stands for Long Range Wide Area Network, and Wi-Fi are two distinct wireless communication technologies that serve different purposes in the Internet of Things landscape. Here are some advantages of LoRaWAN over Wi-Fi. Long range. LoRaWAN offers significantly longer range compared to Wi-Fi. LoRaWAN can cover several kilometers in outdoor environments, while Wi-Fi typically has a range of up to a few hundred meters. This extended range is advantageous for applications that require connectivity over larger areas, such as smart city developments or agricultural monitoring. Low power consumption. LoRaWAN devices are designed to operate on low power, enabling long battery life for Internet of Things devices. They can operate for months or even years on a single battery charge. In contrast, Wi-Fi devices consume more power, which can lead to shorter battery life, requiring frequent charging or larger batteries for sustained operation. Cost-effective deployment. LoRaWAN operates in unlicensed frequency bands, eliminating the need for expensive spectrum licenses. This makes it cost-effective for deploying large-scale Internet of Things networks. In contrast, deploying Wi-Fi networks often requires purchasing and configuring access points, which can be more expensive, especially for wide area coverage. Wide area coverage. LoRaWAN is designed for wide area coverage and can penetrate buildings and obstacles more effectively than Wi-Fi. This makes it suitable for applications that require connectivity across challenging terrains or urban environments with numerous obstacles. Scalability. LoRaWAN supports scalability for large-scale Internet of Things deployments. It can handle thousands of devices connected to a single network, making it ideal for applications that involve a vast number of sensors or devices. Wi-Fi networks, while capable of supporting many devices, may face limitations in terms of scalability and dense deployments. Low data rates and small packets. LoRaWAN is optimized for transmitting small data packets at low data rates. It effectively transfers small amounts of data periodically or sporadically, making it suitable for applications where frequent, high-speed data transfer is not required. Wi-Fi, on the other hand, offers higher data rates and is better suited for applications demanding real-time, high-bandwidth data transfer. Interference tolerance. LoRaWAN uses a spread spectrum modulation technique that provides better resistance to interference, allowing for reliable communication even in noisy environments. Wi-Fi, operating in the crowded 2.4 GHz or 5 GHz bands, may face more interference from other Wi-Fi networks or devices. It's important to note that LoRaWAN and Wi-Fi serve different purposes and excel in different Internet of Things use cases. Wi-Fi is typically more suited for local area network applications with higher bandwidth requirements, while LoRaWAN is well suited for wide area network applications that prioritize long-range coverage, low power consumption, and scalability. The choice between the two technologies depends on the specific needs of the Internet of Things deployment. Now let's go over here and give this article a read. LoRa, combined with BLE, creates complementary hybrid Internet of Things connectivity. When it comes to connecting Internet of Things devices, there is no one-size-fits-all protocol to address all use cases. Each connectivity option has trade-offs between power consumption, bandwidth, and range. Fortunately, users can now combine both long-range and short-range connectivity as a hybrid module. Integrating LoRa and Bluetooth Low Energy creates synergies that maximize efficiency while producing a low-cost infrastructure. I'm going to leave up all the links in the description for those who would like to keep reading.